In this video, we'll be looking at graphing the cotangent function. So graphing the cotangent function, given that it's the reciprocal of tangent, really just modifies where specific values will end up being. The way that I'm going to make note of this is the fact that if I have a value ends up being 0, it's technically 0 over 1. If I were to flip that value, it's going to be 1 over 0, which creates an asymptote. And very much like that, if I have an asymptote and I were to flip that value, it would become 0 over 1. So really, if I'm going to graph the cotangent function, I really just have to graph the tangent function and flip all locations that are asymptotes into zeros and all zeros into asymptotes. So that's how this is going to build. Now what's really nice about this understanding is that this is also true for secant and cosecant. Remember, cosecant being the reciprocal of sine, meaning that everywhere that there's a 0 for sine or an asymptote for sine, it's going to flip vice versa into an asymptote or a 0. So for cotangent, I really just have to understand how tangent is graphed. Well, if that's the case, I know that tangent's initial amplitude is going to, again, not really be an amplitude, but be the anchor point of a height of 1. My period is going to be actually 2 pi, and I don't have any phase shifts. Sorry, not 2 pi, pi. So that my end point is pi. I'm going to cut that in half and get pi over 2. I'm going to cut that in half and get pi over 4. Multiply that by 3, get 3 pi over 4. And then finally, my 0 location. Now, originally, the tangent function originally had a 0 here, a high point here, an asymptote, a low point, and then 0 again. So again, if I keep that logic in mind, that every 0 becomes an asymptote, and every asymptote becomes 0, the 0 that's here will actually become an asymptote. The 0 that's here will actually become an asymptote. And the asymptote that was at the center point is now a 0. The original other 2 points don't get modified, because if I try to flip 1 that's divided by 1, it's still 1 divided by 1. It's still 1, so that doesn't change, and negative 1 over 1 still doesn't actually change. So this location is still going to be a value of 1, and this location here is going to be a value of negative 1. And again, I'm going to avoid graphing that. I'm going to avoid plotting those points until I've graphed the asymptotes, just because I like to have the curve as appropriately smooth as possible, and I've already made that slightly off, but that's okay. It'll still look like a cotangent curve, such that it's got a high point here, a so-called high point here at 1, and a so-called low point here at negative 1. And that right there is what cotangent in its basic form is supposed to look like. Again, recall, what I am doing is I am graphing tangent in my mind, and I'm taking every asymptote location and turning it into a 0, and taking every 0 location and turning them into asymptotes. So I really don't need to know what cotangent looks like, other than the fact that if I know what tangent looks like, I flipped asymptotes to zeros and zeros to asymptotes. All other points remain constant. So that means that all the information over here, my amplitude is really just A, the absolute value of A. Again, no real amplitude, just a high or low point. My period is really going to be that pi divided by the absolute value of B. And my phase shift doesn't change either, it being negative C divided by B. So these values still hold true to the original function we were talking about. So if I go ahead and try and graph a cotangent function, let's go ahead and do y equals a negative 2 cotangent of, let's do 1/2 x. And again, we're not going to do a phase shift in here because I don't want to make things too complicated this early in the set of videos. But just remember that the phase shift is simply going to be a step that's additional to the cotangent graph. So you do your amplitude value of 2, remembering that the negative is actually going to be flipped vertically. My 1/2 value is really going to be part of my period originally being pi divided by 1/2, so that's going to be really 2 pi. My phase shift doesn't exist here because it's technically going to be a value of 0 with the plus C, so 0 divided by anything, so again you could write 0 or none. And again, if it asks you for a phase shift, you have to make sure you state that there isn't one or that it's 0. So now let's go ahead and graph this cotangent function. Now again, when I go ahead and graph a cotangent function, I'm going to start here such that I go ahead and do that 2 pi at the last point, cut that in half pi, cut that in half pi over 2, multiply that by 3, 3 pi over 2, and then finally this location here is 0. I'm going to make sure that I note one more time that my amplitude values, again not really amplitude, but high and low points, I'm going to actually label them this time. And then what I'm going to do is I'm going to go ahead and in my mind I'm going to view the original tangent function. The original tangent function, I'm going to put x's here because I can erase them afterwards. It was 0, so-called high, asymptote, so-called low, and 0. That was my tangent function. So if I'm going to do my cotangent function, I'm really going to have in pen an asymptote here, an asymptote here, and a 0 point here. So I've identified those points based on it being cotangent instead of tangent. Now the last thing I have to do is worry about this negative. The negative is just going to take these locations where I put x's and it's going to flip them to the other side. So I should have a point, give or take, here. Again, it was here, now it's going to be down here. And instead of having the x here for the tangent function, the cotangent function should land somewhere approximately there. And I should do a very careful job of sketching this graph to be a nice, smooth curve. Again, making sure the arrows are on the end of it. And that right there is your cotangent function such that it's flipped vertically. It has a period of 2 pi with no phase shift and an amplitude of 2. Again, notice how it looks very much like this, except for it's simply upside down. This is the generic cotangent function. You can memorize the 5 anchor points being asymptote, high, 0, low, asymptote. Or you can be lazy, memorize the tangent function being 0, high, asymptote, low, 0, and then remember that every asymptote becomes a 0 and every 0 becomes an asymptote in these reciprocal functions. So this is also true for secant and cosecant. So in that case, if I do a really quick sketch down here, we can do some more examples of them in another video. If I look at y equals the cosecant of x, that means I'm taking the sine function, 0, high, 0, low, 0, and I'm going to go ahead and take every 0 point and I'm going to turn it into an asymptote. So my cosecant function should look like this in its basic form. So I'm going to have an asymptote, I'm going to have the high point, I'm going to have another asymptote, I'm going to have a low point, and I'm going to have a third asymptote. So again, every 0 in this function becomes an asymptote, and then every non-zero point stays where it is. So the question becomes, well, what does the function do at those 2 points, given that this curve used to look like this? Well, it can't touch these asymptotes, and again, the concept is the cosine of x can't ever actually equal to 0 because of the way that the function is built. So in this case, instead of it coming down like this, it's going to come up. And it's going to come up. It's going to go in the opposite direction of what the original sine function looked like. So it's going to look like this, and it's going to look like this. Again, away from the direction it was headed. If it helps, again, take a look at this in pencil, sine curve in the middle. It's doing opposite of that sine curve is doing because, again, all these values were fractions, but when we flip them, now they're getting excessively larger. So that's your cosecant function, and we can do the same thing again for secant of x, such that secant focuses on the cosine function, so it's high, 0, low, 0, high, making sure that, again, I do a nice smooth curve of this graph. That's what the cosine function originally looked like. Sorry, this should correlate over here, and this is going to correlate to what's the one over here again, because this is cosine. So the secant function is going to take all those 0 locations, and it's going to turn those 0 locations into asymptotes. It's going to leave the other values alone. So it's going to leave the 1 at 1. It's going to be an asymptote. Then it's going to be the low value. Then it's going to be another asymptote. Then it's going to be back up to the high value. And we've got to remember that originally this is what the graph looked like. So if I were to sketch that in pencil here, again doing a poor job this time to make it look curved, we should understand that the graph is going to go, again, these are all technically fractions, in the opposite direction. They're going to get larger. If they're negative, they're going to get more negatively large. So for the secant function, it should be 3 pieces. We just have to remember, again, that this function technically continues on forever, again, going like this, such that we have another asymptote, and so on and so forth. But these are the main 3 pieces that have to be graphed to sketch the secant function. Again, the most important piece of understanding is for the cotangent, the secant, and the cosecant, we are graphing the function in relationship to sine, cosine, and tangent. So if we feel comfortable graphing sine, cosine, and tangent, then all we have to do is add one extra step where we take the zeros and turn them into asymptotes, take the asymptotes, turn them into zeros, and leave all other points more or less where they are supposed to sit. And that will give us, again, what the function is supposed to look like as secant, what the function is supposed to look like cosecant, and what the function is supposed to look like in terms of cotangent.